Yeah, I think we can start now.
Okay, great. Okay, so good evening, everybody. Uh, last night we finished about the first uh, one third of this slide deck. That's for lecture 5, right? So today we're talking about continued as lecture 6. So I combined these slides together because these cover almost the comprehensive things about the defect, junction, and home junctions. Okay, so we basically discussed, metal semiconductor contact and how to draw the junctions, how to draw the band structures, and how do we determine whether they are ohmic contact or Schottky contact. Okay, and then before that, we also show you how to plot the band diagram for p-n junction. So today we are going to show the process or the method to plot the PIN junction, okay? Because PIN junction is another important junction or structure people use to fabricate solar cells. Some examples including amorphous silicon solar cells, GIAN solar cells, or these 3-5 solar cells basically are made of PIN junctions. Okay, with that, PIN junction basically have what? You have P layer, and then you have I layer, and then you have what? You have N layer. Basically, the P layer will transport what? Transport the holes, and then N layer will transport electrons. The I layer is the active materials that absorb the sunlight, right? So if you think about the perovskite solar cells, right, you also have, PIN structure because you have a whole transport layer that's basically P type. Then you have perovskite that's I, then you have a electron transport layer that's either one of PCBN or zinc oxide, titanium dioxide, or these are N type. Okay, so that's also PIN structures. So the PIN structures, that's the device structure, right? Now, if you look at the space charge regions, that will happen in the I layer, okay? That's happening in the I layer, okay? And then typically, since the I layer is called I because what? Because intrinsic, you do not dope that N type or P type, so that's intrinsic, okay? So if you form the junction there, that junction will be from what? Okay, that junction will be right, from the P to the N side. And then actually that junction will be, on the P side, the phone junction PI, N side, the phone junction IN, okay? That's why the depletion regions will be happening here. Okay? But the depletion region basically happens as interface, okay? As the P, just the interface between the P and I, also at the other interface between N and I, okay? You can understand this in a simpler way. Simpler way. You think about there's what? There's a capacitor. Right? Capacitor you have two metallic plate. You have two metal plate, and two metal plate, right? Then you have what? Have the gap in between them, either air, right, or either other dielectric materials, right? And then think about if you apply what? Apply the voltage across this capacitor, what happens there? You see the voltage or what? Is the depends which side you apply the positive elective. That if the apply voltage, the positive elective there, you see the potential will goes not potential, the electric field or something, This what is this? This is the potential. The potential reduce, right? Reduce, slowly reduce from V. That wave that's one, and then from 1 to 0, right? Across that capacitor, and then this is for V potential, and then if you think about the electric field inside the electric field inside this capacitor, that's basically the voltage divided by D, right? So you see that the electric field is a constant, okay, constant. So that's basically almost the same concept when you have PIN junction. You can think about the P as a metal plate, the N is a metal plate. Inside the PN junctions, PIN junction in the I layer, you will have almost flat electric field. Okay, and then the potential drop is similar. Will be linearly dropping. Okay, that's what you see here. So that's if I plot that, you can see. Let me remove this. Let me remove this. You see on the P layer, you have what? You have EFN, Okay, that's the P layer, right? That's the EFP. Okay, correct this. There's a typo there. Okay, this is a P. Okay, this is N. Okay, that's what's written wrong. To That's EFP on the left side, EFN on the right side. Okay, and then as we discussed last right my time last night, you guys this morning, right? You see when the phone junction, this EFP, EFM will be aligned with each other, right? So that we go next slide. You see that's basically different color here. You see this one will get flat, right? Get flat. That's basically EFN will move to here. This move to here, right? And then that EC will be moved here, and EV will be moved here. That's what they see here. EC, you see the EC is here on the left side. Once it's become flat, right? The whole EC EV move down, okay? And then if you collect them together, this what you see what inside the I layer, okay? Inside the I layer, you see the potential drops, and then the electric field is almost constant. You have built-in potential, built-in potential divided by what? The distance, the thickness of that I layer, you get the electric field, which is almost constant, okay? So that's what you see here, okay? Now the electric field is from left to right. The reason is that uh, the same concept as we discussed before, because on N side you have a lot of free electrons, negative charge, right? On the P side you have a lot of free holes, positive charge. When this whole positive charge from P side recombine with this negative charge from the N side, what is remaining there? The ions, right? So that's on the N side you have a lot of what? You have a lot of positive ions, right? On the P side, because you lost electron, you lost holes, right? You lost positive charge. So you have what's remaining? Negative ions, right? Negative ions. See here, since this positive, this negative, that's why electric field from what? From right to left, okay? That's what it is. That's different from the capacitor I mentioned earlier, because capacitor, you apply the positive on the left side, okay? But here, this positive is made from the inside because the inside lost negative charge. So only the positive ions left there, okay? So that's how you see the electric field is from right to left. The potential will be higher on the right side, and from the right, the positive on the right side, negative on the left side. Okay, so that's it. I think this we just talked about, right? This things we just talked about, almost equivalent with a capacitor. So typically, if we want to, I think as we all know that if we want to find out electric field distribution in the junction, or we want to find the potential distribution or energy distribution in the junction, we start with what? We start with the charge, right? The charge distributions. That's why there's an equation, very famous equation, useful equation called what? Poisson's equation. So Poisson's equation basically tell you if you do secondary, derivative of this potential or energy, right? This here is actually the potential, right? The energy, okay? Here's the energy, okay? And then if you do the secondary, gradients of this energy or potential, right? The potential multiply the elementary charge E is energy, right? So that's a similar thing. That's equal to the charge density divided by the you know dielectric constant. That dielectric constant here is the actually is epsilon naught multiply epsilon r. Okay, that's also can call what permittivity of the medium. Okay, so you see here the phi is the potential, and then this is what activity, the dielectric constant, Then rho is here is the charge density. Okay, that's it. So if you start from here, you do integration, right? You do integration with x, right? If you see this 1D with x, right? And then you basically get what? You basically will get, right? It's what's the gradients, right? One gradient with minus one. Rho over is x. Yes. And then basically you see gradients of the potential is what? The gradient potential, if we divide by the gradient, that's gradient over the distance, right? X. V over X, V over D. That's basically what? Electric field, right? So this is electric field, okay? Electric field will be equal to what? Integration of this charge density, okay? Charge density divided by the permittivity, and then you do the integration with that, okay? This is electric field, okay? Maybe I should say, okay, yeah, electric field. Make sure this is not energy, okay? This electric field. And then the same thing, if you do integration of electric field, right, you get what? See, this one is D, right? If this D, and then the electric field multiply what? The distance, that's get you phi, right? Phi, okay, that get E times D, that's a D, that's a phi, right? And then that's the same thing. If you do integration again twice, you get the phi back. That's why, here we'll see the do integration of this one, you get what? The electric field, and then to integration of the electric field, you get what? You get the phi, the potential distribution. When the potential multiplies the elementary charge, that's actually what? That's actually the energy distribution. Energy and the potential will be the same thing, okay? So here, there's a few steps in between. You can figure out, for example, E equal to minus, gradient of phi, there's a minus here. That's why this minus become positive, right? Then you do again, and then you get that would be again. Minus E, that's why it's negative, okay? It's negative, this negative, so eventually this gradients of the E, yeah, that's electric field, that's this electric field gradients, gradient of electric field gradients, you get what? You get energy, okay? Okay, so that's it. This is the electric field, and then here is energy or potential, okay? So these are important equations. We want to start with the carrier density, and then we do the integration with carrier density. We get the electric field, and then we do the integration of electric field. We get what? The energy or potential distribution. Now let's take a look at this example, okay? As we just mentioned earlier, right? We have this PIN, right? You see here is a P, it's I, it's N, okay? PIN, okay? Why is PIN? You see here is this NA. On the P side, you have what? You have acceptor, right? On the N side, you have a dollar, okay? That's why it's whenever you see NA, that's a P side. Whenever you see what? ND is N side. Now the question here, why on the P side you have the charge you have there is selective? Because what? Because you're supposed to have buyer negative. You have supposed to have buyer positive electron, positive holes, right? You should have, because you dope that side with these positive holes. That's why it's called positive charge, P, right? Now that the free positive holes recombine with these free negative electrons from the inside, okay? So on the P side, since all the free positive charge is gone, so initially they're neutral. Now only what? Only these negative ions stays, right? Who are the negative ions? Right? That's the you can see that's the boring, right? That's the boring, okay? You can see that can be boring, okay? But the boring silicon will be more like normalized, maybe silicon O2, right? That's the positive, can be the silicon ions, boron ions. But the total will be the same. The total will be the amount of this boring. Right? So in that point of view, you can see on the P side, because you have a lot of, negative boron ions there. That negative boron ions provide you this negative charge. That's why it's Q multiply what? Na, it's a negative charge. And on the inside, since you lost all the negative electrons, so only the positive ions stay. These positive ions is the same amount as the dopant you have. That's why you can assume that is a positive phosphorus. Okay, positive phosphorus. That's why it's positive. This is the charge here. This is the positive. This is negative, right? Okay. With that, now we know the charge, right? If we know left side, the depletion region just as interface between what? The P and I. On the right side, just between what? See, here is the P, this I, right? At this interface. This interface. Here is at this interface. This interface. Sorry, I should. This. I mean the interface just here, just here, just here. Because it's I and wait, and will be on this side. Okay, that's the interface. Okay. Now we know the distribution, right? We know the okay. Now we know the row there, right? This is the row, right? This is row, right? This also is the row, right? We know the row. We do the integration of this what? Of this, use this equation here. Integration of rho divided by epsilon, right? Epsilon is a constant. And then, since this one is flat, right? It's constant, right? That will be just because this guy times what? The xp, right? Times xp, right? So that's what you see there. The electric field will be what? Slowly increase, right? Slowly increase, okay? This electric field, okay? And then, since in the middle of the I layer, there's no extra charge, so that the electric field stay the same as this position, right? Just flat, right? It's constant, right? Constant, right? And then on this side, start from here, since the charge is positive, now the electric field will start to reduce, right? Because the your electric field only stay inside the junction. Outside junction, there's no electric field, right? That's why the electric field start to reduce to zero. See, so here you start from zero, increases, right, and then stay constant, and reduce to back to zero. Okay, that's it. That's something we talk about the amplitude, epsilon. Right? If you think about the directions, you can see decrease to negative, and then stay constant, and then come back to zero. Okay. So now you see this is what this plot here is the electric field distribution. Okay, this plot I plot here is the electric field distribution. Now if you do integration of this guy, right? Do integration of this guy, you basically find out what? Something here. You basically find out the area, right? The areas inside this region, because this guy multiplies the distance. That's the integration of what? Everything here, this do another integration, right? That basically do integration like this, right? If you do integration, basically it's the areas, right? The area inside, right? That tetraloid, right? Tetraloid, right? Okay, that's what you see there, okay? And then that you do that integrations, you will figure out, then something like this. See here, because this one is linear, right? When you do linear, it becomes parabolic, right? Parabolic, right? That's why this positions is here from here to there. This will be something like this, parabolic, okay? And then here, since it's flat, it's constant. Constant multiplied the distance is what? It's linear, right? It's linear, okay? Now again, from here to here, now you have this what? It's linear to integration, and then that's if the x become x squared, right? X squared or negative x squared, something like that, and then you get another, parabolic, right? You see that? Parabolic, linear, and then parabolic. Yeah, that's because you do integration of this guy and then flat, and then do integration of that. That's what you see there. Okay. So with that, you can find out the electric field. Electric field is this big. Then electric field is this big. This will be equal to that at this position, and then from zero increase to that, and then now decrease from here to zero. Okay. And then on the potential side, the potential always decreases. That increases, right? You can see it increases. Okay, see this positive, this negative. Okay, and then you can see potential increases. When the potential increases, they can go deeper. Okay, go deeper. That's what they see. And then you add all this together. This one is here for that, right? And then the middle one is for this, and then this guy is the parabolic for this one. So add the three range together, that's be total VBI, okay? That's the way we calculate total VBI. So this total VBI will be the maximum, open circuit voltage you can get. Okay, you can get. So that's about the PIN. I know we spent quite a lot of time here, so that I try to help you to understand that start from the charge density, to integration of charge density, you get electric field, and then to the integration of electric field, you get what? The potential or the energy distributions, okay? So that's it. This is how you plot it, right? Your PIN, and then this is your depletion region on the P side, depletion region on the drain side, N side. This is where you get what? Negative extra charge, right? This is the charge, right? Charge. And then you do integration of this charge, you get the electric field, and then you do integration of the electric field, you get what? Get the potential distributions. Okay. So with that, now let's move ahead. Sometimes regularly we think that depletion we think is when we talk about depletion, right? For example, this depletion. What does that mean? That something is depleted, right? Something is gone. Okay. The depletion means the free carriers is gone. If you do that, with boron, you bring positive charge there. Do that on the other side would be the phosphorus that's bring electrons there. These free holes and free electrons, they are depleted in the depletion region. Okay, that's what it means. But in a rare case, for example, if the junction is like this, junction like this, junction, right? See here. We just see inside here, everything is depleted, right? This one is this would be the N, this is the P, right? P side, right? The positive charge is gone, negative ions stay, negative ions stay. That's what you plotted, right? This also helps you understand what's going on. Okay. This is a separation between them, right? And then the depletion is not happens uniformly, right? Close to these regions, right? If you think about close to here, it's not fully depleted, okay? Close to here, it's not fully depleted. In the center, they are fully depleted, okay? That's what is this slide about, right? As you go, see here, if this N, right, this is the P. As you go these directions, at the beginning, you are not fully depleted. Only as you go deeper, and then go to here, the electrons are fully depleted, right? And then if you have a holes, it goes to here, the holes are fully depleted, okay? That's it. When it gets closer to the P, the hole is not depleted. When it gets closer to N, it's not depleted. Why is that? We can see what is this slide about. Okay, look at this slide. Look at this slide. What do you see? I'm gonna repeat. Basically on the inside, you have what? You have N9 there. You have N9. N9 equal what? ND, dopant concentration, right? That's actually if you use the EF, EF reference, the carrier concentration reference here, the reference, and then you use that as reference. Use this position, the electron concentration as reference. That's equal to NC, NC, EF what? EF minus EC, right? This EC is the reference. Because after the interface, the EC increases, right? That's why I see here EC is reference, just stay here. As you go deeper into the junction, this EC, get higher, okay? That's why I use this position as ECF, okay? When you get closer to here, look at these positions. Now this N is equal to NC EF minus EC. That EC is here. See, this EC is here. This EC and this EFC, these are different. There's a difference between them, right? The difference between them is called delta E, okay? That delta E. That delta E will be a fact, As they go deeper, that electron cannot go inside, right? Because the electron will be on high energy state. They have to, summarize down, or they have to care by something else, okay? So that's why, on the left side, if you use ND, on the left side, if you still use ND, okay, that's NC, now ND, right? Look at the ND is here. So there's a lot of equation here, don't be confused. The equation was come from different point of view. This ND, because here is N9 is ND, right? N9, the majority carriers, That's it from the is the same as carrier concentration, right? So that's why ND multiply E power minus. Look at here is a minus. This is minus. That basically as the energy as energy level go up, your carrier density reduces, right? Reduces. That's what it means. Okay. And then the same thing if you look at here, the Hall concentration, the Hall concentration here is higher because the Hall like to flow up, right? That's why Ni square over D, that's the P9, right? P9, you have a lot of P9 here. As you go deeper to the inside, the P9 reduces, right? The P9 reduces, okay? That P9 equal to what? Ni square over ND, D, right? Or ND, okay? Oh, that's okay. I'm sorry. This one would be okay. Maybe I should not. Okay. I need to restart this because I already used P9 here on the right side. That's it. P9 is my minority carriers on the N side. Okay. If I see my P9 on the majority side, on the P side, that'd be different. Because I already used P9 here, I cannot use P9 there. So I need to start from P9 here. P9 equal to Ni square over what? Over Nd, right? Nd, this Nd on the dollar side, right? Because I know my N, right? That's N is Nd. And I can count my P9. As my P9 goes to higher, to the P side, I get higher concentration because as energy goes higher for holes, it's energetically variable, right? So that's what it means. That's why this guy multiply this is positive. See here is positive, right? When electron goes to top, it's negative, right? It's negative. You see that difference? That's the difference, okay? And then with that, if you with that you already know, the electron contribution, hole contribution inside the junction, then you can compare that, right? N here is this N, and then compare the ND here. Okay, I'm going to, so the points here, I want to compare the electron concentration here with the electron concentration here, okay? If you compare that two data points, you will see that's equal to this, okay? That's why you write here is this ND multiply that. I'm sorry, ND, yeah, multiply, that's right, okay? The same thing you can do ND, multiply this negative, the same thing is positive. This negative for electrons because it gets harder to go move up, but for holes, if you compare this position, get easier to go up. That's why this is positive and or negative for electrons. Okay, I hope that's clear. And then just consider here, if you add all the positive charge and then cancel all the negative charge, you see here, you have this that position, right? You have positive charge ND, right? ND plus. Why? Because why have ND plus? ND plus because what? Because on this side, you remember all the negative charge is gone, all this positive. This is actually a positive what? Positive ions, okay? This is the positive ions, okay? The ionized, phosphorus. And then here, the holes inside the junction, right? Holes inside junction. Use these positions. That's exactly, this is the hole. See, that's here, right? Then, there's still, some positive charge ionized as ND is ionized, dopant, right? And then the negative charge is what? Is N, majority carriers inside, right? In this majority carriers inside. So that's it, maybe we should think about, okay, I think that should be fine. This should be fine. You have the positive ions, right? Plus the positive charge minus the negative charge. That's equal to total charge you have. If you calculate that, that's about 86% of positive ions. Okay, 86% of positive ions. What does that mean? That means there's still 14% of what electrons that are not recognized. That's a lot depleted. Okay, so the slides here basically tell you, when the electron goes too high into the junctions, the depletion regions, the electron concentration gets slow, get smaller, get reduced. But the hole will go opposite, right? Hole when they get to deeper from N to P, the hole get higher. Okay, and then in the junction, right, the positive ions, that's Nd, right? And then the positive, charge is the P. Then the negative charge will be the electrons, right? Majority electrons. You just add these three together, and then you can find that they are not fully depleted, right? So here it just shows the same thing, right? You see, start from here, now get negative, right? Reduce, right? Right. If you start from the hole here, and then here is positive, right? It's increased. Okay, that's it. You can do the same thing on this side, on this side. So here we talk about here we talk about from N to P. Here we talk about P to N. Okay, it's same. Okay. Uh, so now I think at the beginning, right? And remember, maybe the first lecture, some students ask about type bias. I think we already explained that. Actually, applied bias to solar cells is the same as what you apply bias. I mean, here is the electric bias. If you apply the electric bias like 0.5, like a 0.5 V, different color 0.5 V, and then if you shine the light here, you can also generate 0.5. So the 0.5 V. See here, from this to here is 0.5. From here to here is 0.5. Is 0.5. The same thing. You can do the same thing by apply the light, right? You see this, band structure split between the EFN, EFP is identical, right? That's why what I said, when you apply the bias there, you try to identify where's the maximum power point. Not you apply, it's not the solar cell has not be function, has not be under operation with the electrical bias. You do not need electric bias, okay? That electric bias is the same thing from the optical bias. So next thing I'm going to talk about the defect, okay? Defect is a big thing, right? A lot of semiconducting devices. The defect you think about, I think also students ask questions, right? You have bulk defect, you have what? Interface defect. If you think about the bulk defect, that's basically, the defect will be happened inside the bulk, right? And interface defect happens at interface. That also depends on what? Depends on how you prepare your samples. For example, if you prepare the PN junction, this is P, right? This is M by diffusion, right? Since you already have a very good single crystalline silicon, you diffuse, faster from the top, diffuse, bottom from the bottom, right? And then you do not have you have very good interface because the interface is from the same materials, right? You have very low defect densities. Now, if you use different way, you use, if you deposit one material on top of the silicon wafers, for example, if you deposit zinc oxide, germanium on top of silicon, then that interface defect will be huge because you build new materials on top of the existing materials. Chemical vapor depositions, right? Sputter, evaporation, and then that's will create a lot of interface defect. Okay, when you talk about the interface defect, you basically talk about this interface, right? Interface the PN, right? This is a N. I'm sorry, this is P, right? Okay, this is P, right? Because it's how can I know this is P? Because female is close to what? Close to EV. This is P, this N. Okay, and then the junction is here. Oh, the interface there. The interface best between the two materials, right? There they contact each other. Okay, that's the interface. There are a lot of defect interface. And then I would like to define a few terms here. Typically for the interface defect, okay, interface or interface defect. Now you see the center here, the halfway, above the halfway. Now the halfway is EI, right? Above the halfway, you define that as acceptor like, What does it mean? That means when this state, because this state, are above EI, right? Above EI. Under thermal equilibrium above EI, that means what? If the intrinsic, right, that's also above EF, right? That means they are what? They are not filled, right? They are not occupied. They are empty, and then they are neutral, right? But when you charge that, they become negative charge. Okay. When you charge them, they have to take electrons because when they are neutral, when they are not occupied, they are neutral. Okay, that's why you call that acceptor like because they like to take electrons. Okay, and then below the EI here, all this you call the dollar like because what? Because now because they are below the EF, right? So they are basically filled by electrons. So they are occupied by electrons, right? When they become charged, they have to lose that electron. So they become dollar. When they charge, they have to give electron to others. That's why they call dollar-like, okay? Don't be confused. So above EI called acceptor-like, below EI called dollar-like. That's the reason, right? That's the reason. See here, when charged, they accept electron. When charged, they delete electrons. That's the reason. Okay. Now let's take a look at this example. This is the interface defect, okay? You see if my EF is here, this is my EF. My EI is here, EI is here, see? This is my EI, right? Okay? My EI. See, my EF is above EI, okay? And then you see, above EF, these are empty state, right? They are neutral, they are empty, okay? Then below the EI here, they are also neutral, but they are occupied. They are filled with electrons. How about between? Yeah, between this position, this is an interesting region. Okay, in these regions, they are EI, right? By definition, they are neutral, right? But now since they are below EF, so they are occupied by electrons, right? Now that region is what? It's a negative charge, right? They are neutral when they are empty. Now they are filled with electrons. So that's why they are negatively charged, okay? They're negatively charged. They are acceptor, okay? So got it? Now these regions are, if we have asked you regions 1, 2, 3, which region is what? Is negative charge? You need to tell me that's a 2, okay? That's region 2, okay? That's what it means, okay? That's why, if you think about regularly, the N side, if you look at this is the N side, right? N side, this is the P side, then QND times multiply the XN, that's equal to QNN multiply XP, right? That's what we discussed before. Now, since you have this interfacial charge, that's selective charge, right? You have to add that to what? To the P side, because P side you lose positive holes, there's only what? Negative ions left. So this special charge plus the negative ions, that should be equal to what? To the positive ions, okay? That's what it means. So if you do that, you plot that, the charge density will be different. On the N side, this N, this is P, right? The N side is the Q and D, but at the interface, you have a lot of negative charge, right? So that negative charge should be added to what? And to the P side, because P side, you lost the positive holes, only negative ions stay. Negative ions plus that QI, interface negative charge, negative electrons. Then that's what you get is what? Total charge. Well, this should be equal, okay? If you plot this, now they are not continuous. There's a step. See this step, that step, because suddenly you have negative charge there. That's why it goes down suddenly, okay? Instead of it to slowly reduce to 0, the electric field now is suddenly reduced to that. Because of what? Because of this interfacial, charge, okay? That's it, okay? Now, if you look at these examples, right, you can see if I plot this, okay, see here, okay, there are a lot of things I did not mention here. Now, whenever you look at this one is called surface defect because that's the interface, right? The interface or interfacial defect. This one is called bar defect because go anywhere inside the bar, okay? So you should know that, right? If this is my EF, this is my EF, this is my EF. So everything here is what? Should be what? Everything here is neutral, right? Because they are above EF, right? Above EF. And then these regions should be what? Should be negative charge. Why? Because they are above EI, they are defined as acceptor-like. They are neutral when not occupied. Now, since they are below EF, they are occupied. So that's why this is a negative charge, okay? The same thing here, if you look at here, if you want to understand why, why these regions are positive charge, because these are below EI. You see EI is here, EI below EI. They are supposed to be dollar-like. They should be occupied by electrons when they are neutral. Now, since they are above EF, right? They are above EF here. Now they lost their initially occupied electrons, and then they become positive charge. Good. Okay, that's how you understand. The same thing here. This part will be what? Because they below what? They below EI, they should be neutral when occupied. Now they are above EF, Fermi level. So they lost that electrons, they become what? Positive charge. Okay, positive charge. I hope you can understand this, okay? If you have questions, we can discuss later, okay? So this question just basically answer that question. So which trap state are positive charge is here, right? It's here. Because this should be neutral, right? When they occupied. Now they lost that electrons. The occupied electrons, they become positive charge because they are above EF, okay? Above Fermi level, okay? That's it. So the answer is what? 4, right? It's 4 here, okay? So that's it. The next thing we are going to discuss will be the, let's see what time. We should have time here, okay. Because today you're going to have the demo for the fabrication, so I don't want to take too much time here. But we're finished at 10 o'clock. My time is 10 o'clock, okay. So energy lab, here talk about the ground boundaries, okay, ground boundaries, okay. Ground boundaries is one of the major, defect sources is in this, multi-crystalline materials or polycrystalline materials, or the nanocrystalline materials. In all these kind of, you have small regions of crystals, and then between this crystal domain and next crystal domain, the defect, between them, that's green boundaries. See here, these are green boundaries, right? And green boundaries, see here, greens, that's the green boundaries, okay? That's it, okay? So with that, how can we understand the green boundaries? That's exactly, you can see the interface, right, or surface defect. So you use the same concept we just discussed, halfway above, you call the dollar-like, halfway below, halfway above, you call accept-like, halfway below, you call dollar-like, okay? Okay. Now, if this is a N-type, right? N-type because the film level is here, film level is here, it's this guy, it's this one, okay? Film level is here. Now, above this should be what? Neutral when it's empty, right? Now, since they are below film level, this side is all occupied by electrons, okay? When this occupied by electrons, you can see in this interface, you have extra electrons, right? When you have extra electrons, you push the potential up, okay? Push the potential up. That's why when this N-type, your plot is like this, okay? Your plot like this, okay? Your plot like this, okay? When the P-type, your plot is opposite, okay? If there's P-type, okay, now let's go back to the P-type, okay? P-type. If the P-type, see here, the Fermi level is here, right? This is your Fermi level, okay? That's your Fermi level. And then the EI is here, EI, right? You see, EI, that should be all neutral when it's occupied, right? Now, because of these regions above EF, they are what? Empty, right? They lost that electron. Now, all these are occupied whole by whole. When you have more holes as S interface, the band structure push down. See, you see push down. Okay, that's what I mean. Okay, that's why help you to understand, because this can be very confusing. If you do not understand what it physics behind, you do not know why this push up, for N-type, why this push down for P-type, okay? I'm trying to, give you some explanation, tell you the physics, so in the future, you will never be confused, okay? That's it, okay? So with that, I think we already talked about this, right? We talked about, these things, and then talk about this part is occupied by electrons. That's why this pushed up. Okay. The next thing you want to know, what happened for the electric field in between, right? Basically, right, there's this one junction, right? This junction here you have positive, here's positive, right? Positive, positive, right? Positive, positive, right? Because this is what N-type, right? N-type, you lost these free electrons. You have only positive ions left, and then you have some negative, charge trapped there, right? This trapped charge, that's why you form electric field, from positive to the center, and then again it changes directions, and then from negative to positive. So that outside the electric field only happens inside, they cancel themselves, That's what it means. Okay, so with that, I think you also want to know, how you can calculate the barriers, right? If the electron try to pass through, or hole try to pass through the ground boundaries, how do you know how much is the barriers, how much resistance you have there? Okay, so one of that is you will do the same thing, right? You find out the charge density, you do integration of the charge density, carrier density or charge density. you get electric field distribution, and then to integration again of the E, you get what? Potential, right? Potential, okay? This is like a general way. Everything you can use that, okay? We talked about that earlier, okay? Now let's see, okay, since this is N-type, right? This one is N-type, okay, N-type. So the charge you have there is what? QND, right? QND, the dopant, or the, let's assume all the dopant is ionized, right? And then you have positive ions and QND on the left side, on the right side. In the center, suddenly, because you trap a lot of electrons there, the electron is selective, so that's why it goes down, okay? Then you do integration of this QND, right? What do you get here? The areas here, that's QND multiply what? Half W, right? Half W, right? I see here QND multiply half W divided by what? Epsilon, right? Because you do integrate of rho and then also divide by epsilon. See, the maximum is there, right? Then you increase from 0 to there, right? Inside the junction, right? And then suddenly everything moved down because you look at here, it's go opposite, right? And then this just, reverse, right? Just go opposite. And then shift everything down to negative, and then this become negative, right? Negative the same, and then slowly come down to 0. You see that? That's the electric field, distribution, right? And then if you do integration of this, since this is linear, this become parabolic, right? Parabolic. This also linear, become parabolic. But this one is negative, so this is why it goes down, right? Because the entire thing negative, so that's why it goes down. It's very clear, right? And then if you do that, you will find out, the VGB, the potential, bare potential of the ground boundaries, that's equal to QND W square over, 8 epsilon R, okay? That's what they have, okay? That's here, okay? So typically from here, you can see, if you trap more electrons, that's basically ND is high, right? ND basically tell you the trapped electrons at the ground boundaries, okay? If that ND goes higher, you know that you have higher, trapped electrons, okay? That ND basically you can understand the trapped electrons. Then VGB will be higher. That block your electron or hole transport, okay? That's basically, those push up more, or if for holes, is what push down more, okay? Push down more, okay? That's it, okay? As you have a higher, if you trap more electrons, this thing keep goes down, okay? Keep goes down like that. So that's about the ground boundaries, okay? There's an example here. You can read this. If you care about these examples, this is see here. What is Q? What is ND? What is W? And then and then calculate. You find at different concentrations you get different pairs as the ground boundaries. Okay. So here's the ground boundaries, for the charge transport. If there's no electric field for N-type, it's like this, right? The ground boundaries, electron travels through, slow down, and then tunnel through or to whatever through, and then again. But under electric field, it can go down like this. The electric field from here to here, then it's go down like this, right? It's kind of a little bit help the electron transport, right? Then for the hole, we go opposite, right? Hole is without electric field is flat like this. Now if you add electric field here, and then positive here, negative here. If your whole transport from this side to that side is good, right? But if whole transport from this side to here, that's not good. The same thing for the electron. This side is good, but it's opposite, that's not good for the electron transport, okay? That's you see how the, how the ground boundaries affect, okay? Next thing I'm going to discuss will be the charge transport, carrier transport in the p-n junctions, especially the HOMO junctions, right? Now let's see, if you have any any electron transport through your diode, right? Your diode basically made of a p-n junction, right? This is a depletion region, of course, that SCR region, the same thing. And then, outside this depletion region, you call the P side what? Quasi-neutral regions, right? On the N side, the same called quasi-neutral regions. Basically, it's neutral, right? It's dope, right? But you can assume that it's quasi-neutral compared to, region in the center, right? You have a lot of extra charge there, okay? And then the charge goes in, first you will see what? Injection, right? Injection, okay? That's injection. The second one, what you see here will be the diffusion through the N plus layer. The third one, what you see here will be swept over the junction, right? The fourth one here is what? Diffusion through the P, okay? Now, that's why you see the four mechanisms, right? Injection, right? Injection, diffusion, swept through, that's actually diffusion, a drift process, and then diffusion again. you see the full process in order for electron pass through a diode. Okay, that's it. Then the problem here, the diode, you have to add the gate voltage. Basically, you add the forward bias here, right? Forward bias, basically, you improve what? You improve this one. You see, initially they are flat. Now you put that high. When you put that high, see, there's electron here, right? Electron here. It's our electrons, okay? Electron. And then you push electron up, the electron has potential energy come down here, right? That's what you see there. Okay, that's why the diode equation is equal to GIAN, times E QVA over NKT. That's why exponential VA. Okay, when you apply the VA, this VA, that VA push the everything up. That's why electron flow down easily. Okay, it's the same concept. Okay, so here, typically, if you think about the, uh, you know, the transport, right? If you have different mechanisms, some is faster, some is slower, you know that the current is what? Is dominated by the slower process, right? Like you have the water pipe, you first have a larger diameters, later you use a small diameters, right? The smaller diameters of the pipe will determine how fast the water flow. The same thing here, as you see here, I have four process, right? One, two, three, four. Which one is slower? That determines the entire current you have. Okay, you got it. That's what it's about. Then so basically you can see for these kind of p-n junctions, that's typically the diffusion slow down. Then for this one, okay, in the most, okay, let's see what is this about. Quantity neutral regions in most crystalline zones under medium forward bias. Okay. Uh, That's basically if this under medium forward bias, the diffusion dominate. If this under no bias, and then the drift diffusion dominate, right? That's basically for PIN junctions. That's a diffusion drift inside the I layer in the junction, right, between PIN. Okay, then under certain conditions will be injection. So this basically tell you, different device under different conditions, under different preparation conditions, you may have different results. You may find the different, either diffusion or diffusion drift or even injection. You'll figure out which one is your dominating points, okay, dominating points. Okay. So typically, if you look at the diffusion compared to the junction swap over, the junction swap over, especially for p-n junctions, is very fast, very fast. Here's example. Whenever there's a small amount of the gap there, there'll be huge electric field there. That electric field will swap over the electrons from the p side to n side or n side to p side so easily. So that's why you don't worry about the drift current. Drift current basically is the electron hole flow move under what? Electric field, okay? If you calculate that, just assume, there's what? There's the 1 kT difference between the EF and EFP. Then under, normal conditions, you find the current. If you use that current, drift current is huge, right? But in solar cells, you don't get that high current, okay? That's why the diffusion most of the time dominate, diffusion dominate, okay? So here shows, I think after this probably we can stop, okay? Here shows the, how can we develop a model for the diode, okay? The diode, maybe pictures away, picture here. No, not that, okay? This is not the equation. I'm going to show you this equation here. This equations. See this equation? I want to go back to you, show you that, okay? You remember this equation here? Right, the diode equation, right? Yes. Come in. Oh, did they change it? Did they do anything? Oh, I will let you know. Yeah, sure. Okay. Yeah. So if you look at this diode current, right? The diode current here, that's a GIAN, times exponential something minus 1, right? I want to remember this format because later when we, use this carrier density, to develop similar equations for diode, you will see there's similar format, okay? What I'm going to show here, when the diode is not open, the diode is closed, right? There's no current flow. You see that, right? You see the inside EFN, the right side will be EFP. They are aligned, right? And then how much current density on the P side, this, how much current density on the N side this. You see this, right? Is this, okay? Now let's see if I add the forward bias here, VA, that's I push inside up, push everything up here from the left side. And then you see my total electrons I can get from the P side is this much, You see the difference? Okay, let me write this here. Write this. You see this one? Later become this, right? Okay. Because when my diode open, my actual current, my actual charge is what? Is after I add bias, I get more electrons minus, the current I have early, right? Okay? That is why this one minus that's equal to here. You take this one out, that's EXP VA over KT minus 1, right? This exactly is the same thing as this diode current, the diode current, okay? That's actually how you derive the equations for diode, okay? For diode, that's the same thing, okay? So with that, I think this is a good slide. We can stop here because next thing we're going to discuss will be the, how to do the modeling for the diode, how we can understand the diode, whether it's a long diode, short diode, and then how the photo generation in this diode can, help us to understand how solar cells work, okay? That will be something we'll discuss tonight. For my time, your time will be tomorrow morning, okay? So I'm going to stop here and take a few questions, and then I'm going to the lab, and then ask the students to provide the demo for you, okay?
Yeah, thank you, Professor Chow.
No problem.
Yeah. So now, yeah, students may ask the questions if they have any doubt from today's lecture.
Thank you, sir. We have one question from Mr. Sumit. Sumit, you can ask your question now.
Hello.
Yes.
Yes, Sumit, we can hear you.
Oh, sir. Yes, sir. I have a question.
Please go ahead.
Yes, sir.
Yeah, Sumit, please go ahead.
Yes, sir. I have question, sir. As we know, when NN and PN heterojunction form, the Fermi level aligned, है ना? Then work function value always remains same or varies for both material. Suppose one is one N type, yani ZNO, other is a P type copper oxide. So then work function value will varies or same.
Can you repeat the question? You mean the work function on which side? I see. I can hear my echo. Anyway, so the work function. See, you talk about PN junction, heterojunction, right? When the female never aligned, and then you talk about the work function of the P side, N side, both of them, or one of them, or the work function on the materials does not change. The only thing change, is inside the depletion regions. Did you get my point? Outside the, you think about okay, you think about if you deposit For some reason, I can hear my echo. Is there any way to remove my echo here? Now it's okay. Okay, pretty good. Okay, so maybe I should show. Let's go to one of the slides. I have talked about the band bending stuff, and then you have either you can clarify your questions or I can explain better. Okay. I think this is probably a good slide. Okay, let's take a look at this slide, right? This one is what? It's a homo junction, but doesn't matter, right? So can you look at the slides, repeat the question so that I know what is the question about?
Yes, sir.
Go ahead. Go ahead.
Yes, sir. I have question. As we know, when NN and PN heterojunction form, the Fermi level aligned. Yeah. Then work function value always remains same or varies.
Oh, you're talking about the work function for your
Yes, sir.
material, right?
Yes, sir. Both different materials, sir. If someone is anti, whether it's p type, like someone anti with ZNO, p type with copper oxide, heterojunction form.
Okay.
Then
Okay. Can you look at this here? You look at when you talk about the work function, you talk about what? Work function related to the working level, right? You see the working level here, working level. The working level shift. You see this? See this? So in that point of view, your work function does not change. You know what I mean? Your materials will not change your properties. The only thing I can see, if you want to see the change, that only thing change probably inside the junction. Look. If this is a junction, you see now Fermi level is here. You can claim, my work function change in these regions, in these regions it change. In this region change. But outside that, nothing change. In this region change, why? Because you bring extra charge there, okay? Did I answer your question?
yes, sir. I have got my point.
Okay, great.
Hello,
Yeah,
may I audible, sir?
yes.
Yeah. Yeah, my question is related to the slide number 41 and 42.
Yeah, this is 41. This is 42.
Yeah, on 42.
Yeah, this is 42.
Yeah, yes. See, in this one, regarding the electric field profile at the grain boundary, here we have considered that the electric field profile, the no external disturbance, no external electric field we have considered like that.
No, we have not. Right. This one is generated by itself.
Okay, so in the next slide,
Yeah. Now you have
so
electric field.
yeah, if we have find the band notch by applying the electric field. So here we have considered that the electric field throughout for the all the grain boundaries is same. Okay.
Okay. So if you apply electric field, right, let's assume, your electric field is what? The voltage divided by what? The distance, right? So that
Yes.
electric field is the same inside the entire system, right?
Mhm.
But locally it will be different because electric field, there's electric field here, this local electric field and that electric field will add together. But we did not consider that local electric field. We just assume it's this, and then if you add this together, there may be difference there.
Like when we are dealing with the PN junction,
Yeah,
like uh, the bottom material is a microcrystalline and some grain boundary is there. So if that grain boundary lies in the depletion region, so in that region the electric field is very high.
yeah.
So what are the impact on that high electric field on this band bending?
Oh, okay. So so you talk about you apply the, okay. Then the bending would be offset, and then we'll go back to there. You talk about the junction, right? Okay, the junction, I think I
No.
have, yeah. Just a second. Which one I talk about the bias? Whenever you add the bias, you add the electric field, right? So
Yes, yes.
here. Okay, look at this. Okay, see, no, this is a PN junction, right? When you add the bias, you add the electric field, right? You got it? You add the electric field, the same thing, right? So you basically push this EFN up, EFN up, and then the electric field inside will be generated by this guy, by this bias, right? So it depends how high you add your bias there, and then eventually you can put this up flat, and then the left side, the right side, if you push flat, it would happen. That become like this. Look,
Yes.
that's like this, and then it's like this. Okay. And then you see any electrons can go much easily to there, right? You see, because the distance here is the electric field, right? Huge electric field inside. I'm not sure. Did that answer your question?
Yeah. My question is that if the two electric field are both, like the depletion region electric field as well as the electric field generated due to the segregation of the charges at the grain boundary, both are there, then which will be more dominating? Like the band bending will be there or not? Like go to the slide number 43.
Okay. Yeah.
Yeah, like the left portion of the grain boundary, if it is lies in the depletion region.
Okay. Look at here. Here the electric field is like this. Look. This is electric field,
Yes.
You don't have lead electric field. Electric field just happens in, yeah. This one consider this one. I don't know what you mean about the applied electric field there, huh?
No, like when we are applying the electric potential across the PN junction, there is
Yeah.
a high electric field in the depletion region.
Okay, yeah, that one either either you add more electric field to that existing electric field, or or the other way you cancel that. So I don't know what is the point, which one is more dominant. You know what I mean?
Like this type of band bending will be there or not the time.
Okay, for example, if the band bending is there, right, and then you add the electric field the same directions as the band bending generated electric field, you double that, right? Your electric field gets stronger, right? Yeah, gets stronger, okay? If you add the opposite electric field, you cancel that electric field. You will remove that band bending. The band bending will be gone. You know what I mean? That's why I plot here. You remember I just showed here? You have band bending here. Here you have no band bending. You see this? No band bending. You know? So so why do we care about which one dominant? What do you mean
Yeah,
dominant?
okay. Because when we have considered the grain boundary in the main absorber layer in the PN junction solar cell. Okay. So in the absorber layer, we find that when uh, because in the horizontal direction, there will be no variation in the electric field. Generally, variation in the electric field in the vertical direction of the structure. Like here, in the horizontal direction, we will find the variation in the electric field, right?
Yeah. From N to P, yeah.
Yeah, from to N to P, we are finding the variation in the electric field. But
Yes.
on the perpendicular to that one, we are not finding any variation in the electric field.
Yeah, because the electric field is across the device, right? It's not, I mean, parallel to the devices. It's from the N to P, right? That's where the charge transport, right? So you don't care about the inside the N from, one position to next position, right? That's why you add the electric field there. You want to direct all the charge transport for solar cells from P to N, right? For diodes from N to P, that's it, right?
So we found that if we are moving from top to bottom, not from left to right, from top to bottom, then we are finding this type of notch at the grain boundary that you have shown in the slide number 43. In the slide number 43, this
Yeah, yeah.
type of notch we are getting when we are moving from in the structure from top to bottom. Okay.
Okay.
When we are from either perpendicular to the PN junction, when we are moving perpendicular to the PN junction, then we are finding this type of notch. And if we are moving in across the PN junction, then this type of notch generally we are not finding in the high electric field region, the depletion region.
Yeah, that makes sense. What I want to talk about here is ground boundaries, right? That's
Yes.
basically charge transport, right? Now, in your depletion regions, you don't even have charge, right? You know what I mean? The charge there is the ions, right? That's just electric field. It's depleted. There's no charge there. You know what I mean? Whenever you have charge, it's just swept away, right? Swept out right away. So you don't see this phenomenon. This phenomenon more happens in the diffusion, Did you get my points? In the
Yes,
depletion
yes.
regions,
No, I
you
get.
don't have the charge transport. Everything just swept over, right? Because the electric field is so strong, just like tunneling pass through right away, right? You cannot see this kind of thing. Okay.
No,
It only happens in the P layer or N layer, outside the junction. Yeah.
even in the depletion region, when we are moving perpendicular to the junction, we are finding this type of this band profile.
Then that's okay. Perpendicular, you means not across the PN junction, right? It's
Yeah.
parallel, and then the electric field doesn't affect you. So still the transport through what? Through the diffusion, right?
Okay.
This the diffusion or the drifting, only when your electric field will not sweep everything away, you will be able to see this kind of slow kind of processing. Otherwise, you cannot see. Also, when the other thing about the thickness, right? Across the different regions, the thickness is very thin. But if you do like if you turn that like 90 degree, and then your film can be very thick, right? Because you don't care about the crossing, you care about the, what is that, right? In the inside or P side, right? You know what I'm talking about, right?
No, so can you please explain it?
Look, this is okay. Maybe I can just draw the wafer, right? There's a wafer like this. That's wafer, okay. That's a wafer. Okay, PN junction. If you
Yes.
do from here to here, the wafer can be very big. Of course, you'll see the diffusion, you'll see the transport, right? But this direction you cannot see because the electric field is so big, right? You also see this layer is very thin, very thin. If you do from here to here, that's the same thing as you go from here to here, Same concept, you know what I mean?
Yes.
That's why you can see it. If you do that way, you can see it, okay? Yeah.
So like in this structure, when we are moving from left to right, then we are finding the variation in the we are finding notch at the grain boundary.
By the way, I'm just confused. I'm just curious. How can you do that from here to here in the PN junction? You just
No.
make the PN junction very thin, or how do you do it? Otherwise, you cannot marry. You cannot get the tip into the D. You cannot get your tip into the wafers, dig a hole there, and then just test there. I'm just confused. How can you do that? Huh?
No, I'm talking about when I am doing simulation of that by using the Silvaco TCAD.
Okay, simulation. Okay, then that's fine.
Yeah.
Okay. Yeah.
Yes.
What's your
I'm
next
doing
question? Yeah. Yeah.
Yeah, I'm doing simulation in the Silvaco TCAD. So
Okay.
I'm trying to find out the bending in the conduction band and valence band due to the grain boundary. So I found that when we are moving from left to right, then there will be a bending in the conduction band or even in the valence band. This type of notch we are finding that we have shown in the slide number 42. But when we are moving from top to bottom, okay, then this type of notch is not exactly visible. Some slight visible notch is there, but not exactly.
Yeah, I think that's I just explained, right? You you did that inside the junction, right? Inside the depletion region, right?
Even outside the depletion region,
The
when we are
outside
moving
depletion
from,
region, and then maybe the say you do the simulation, right? And then you need to do this, right? You need to understand the mechanism, you cannot mix all this together, You have to do this as we just mentioned, right? Step one, let me do this, okay? You have to either, okay, I go opposite, okay? I want to just use a diode, so everything is, okay, let's do this way, okay? You have to do this injection, step one, right? And then you simulate that, and then diffusion in N, right? Then step two, and then junction step over, step three, right? Diffusion, step four. You cannot mix everything together and then say I got some phenomenon, I cannot get what I want, You have to separate each of these and then you find out which one is a slow process. That slow process will determine the entire, current flow through the entire diode. Okay.
okay, okay.
Yeah.
We
So,
need to analyze these things.
okay. Because you mix everything together, you get phenomena, you have no idea what's going on, right? That's what you see, what you see, why you get confused. Yeah.
Thank you, sir.
Thank you, sir. Can we take one last question from the chat box?
Yes, and then, yeah, sure.
Yes. The question is from Mr. Shahjahan, and he's asking on what conditions the defect states affects energy band diagram. And in another one, he's asking, does defect states always carry charge?
What is the first question?
The first question is asking, like on what conditions the defect states affects the energy band diagram?
On what conditions okay, that depends how much charge you will trap. Depends the charge density, the trapped charge density. If the trap density is so small compared to the current density, and then it will not impact anything, just some disturbance, right? When the charge current density, when the trapped current density become higher, then you will affect the band structure. That's the same thing, the same thing as we just talked with the other student here, right? See here, look at here. This one, can be very small, But by the way, this is not p-n junction. This is just the current boundaries in the n-type transport, right? Don't confuse this with p-n junction, okay? This is not p-n junction, okay? So the band structure is like, you want the band structure like this, right? Now you see it's like this, right? You see like this, right? And then this can be, doesn't matter, right? But once it becomes something like this, that can cause you a problem maybe, right? So this one depends by what? Depends by look at the equation, right? ND, right? This ND, second is trapped charge. You can say N1, right? That's a trapped charge, right? How much trapped charge? How much trapped density? How about what is concentration of the defect density? That effective, okay? That's the first question. The second question is what is the
The second question is asking is like, does defect states always carry charge?
always carry charge, or that depends, whether some trap state is through shadow. Even trap charge is okay, it's trap release. Some trap density get deeper the trap and then the hold the charge there for a long time and then cause problems, okay? So that depends how deep, you know. You have some shallow trap state, some deep trap state. The deep trap state may give you more problems.
Thank you, sir. With this, sir, we are done with the questions for this session. May I request Professor Mahesh, sir, to kindly proceed?
Thank you, Nipun. So now we will move on the tutorial part. So already this one, Raja Sekhar and Poojan, they are here, and they are going to basically show this one how to fabricate these solar cells. So today they are going to fabricate this one PIN junctions. I think Professor Chow can, say.
I'm going, yeah. So right now I'm in my office. I'm going to go to my lab, okay? And then I already sent the link to the students. I will, you know, log out of the meetings. I will go to the lab. The students will use their cell phone or their computer there to show you, you know, like real time, okay? So I will log out right now and I'll go to the lab, okay?
Yeah.
Okay.
Yeah, thank you.
I may not
So
log out.
students, wherever they have the doubt, actually they can ask this one. And
They can ask you questions anytime. They will still use my account, but through their cell phone, their computers, you know, instead of my computer. Okay, they will log in. I may log out and then use their, you know, device to log in again. Okay.
yes, and Professor Mukesh is here again to help this one. He had worked on the solar cells. Yes, Professor. Yeah. Yes.
Thank you, Mahesh.
Yeah. Thank you. Yeah.
Hi, Yuchen. Can I ask, are you able to share your screen?
Yeah, I was going to share my screen. So
Oh, okay, they already joined in. Okay, so I can log out here. Okay, good.
Basically, today they are going to demo this one, how to fabricate the solar cells. So they will tell the steps, basically, different steps, how to fabricate these perovskite solar cells.
I need to relog in to like reset the preference. So I will join like in several minutes.
Yeah, no problem, Eugene.
Okay.
Amit, you please make sure that he has a permission to share this his screen.
Yes, sir. Yes, sir. I have already given the privileges
Okay.
to him as a presenter.
Sure.
Sir, he has logged out. Yes. From the
I think he has some issue, so he might be logging again. So the students for the fabrication of solar cell, so that is a thin film solar cell, as we all know. So there are different steps. So you have starting from the substrate, and then you go for step by step, because this is a thin film. So absorber layer might be about a micron or so, and then this absorber layer, okay, is absorbing the photons and creating an electron and hole pair. Okay, and these electron hole pair need to be separated out at the hole selective layer or the hole transport layer and electron transport layer. And as a perovskite, it's a unique material that is neither p-type or n-type, it's intrinsic. So you need to have the very good interface chemistry between the perovskite and this selective layer, electron and hole transport layer. So that totally actually decide what will be the efficiency of the final device. So Yushan, are you ready?
Yeah, so can everyone see the screen?
Yeah,
The
yeah,
PowerPoint? Okay, yeah,
yes,
so let me start.
please.
So before our real demo, I will just give a presentation of the like basic procedures we will do in the fabrication. So here is like basically what we need to do in the fabrication procedures. First, we need to clean the solar cell samples since we want to make the FTO layer clean so that we can add later layers on it during the fabrication. Second, we need to prepare the fabrication solution earlier than the fabrication. Usually we prepare 1 day before the fabricating since it needs to be stirred on the hot plate for several hours to let the solution dissolve entirely. And in the real fabrication step, we add different layers by spin coating. So you can see on the right, there is a simple graph of basically what we do. Actually, our real fabricating is more complicated. We sometimes add more dopings and we add another rod mean layers after PCBM layers. But basically every layer is by spin coating. And the final silver layer is by evaporation. So here is what we use in the to clean the samples. First, we get the uncleaned samples, and we use the multimeter to check the conductive side and the non-conductive side. The FTO side are conductive, so when we use the multimeter to check it, it will beep up, and when we hear the sound, we know it's FTO side. So we will flit it up to the glass side since we want to label the numbers on the glass side so that we know like which side we are adding the layers on during the fabricating. So you can see in the right figure, there is an uncleaned sample and the top half side is in color. That means they are FTO covered, and at the bottom it's transparent, so they are purely glass. So we will label our numbers on the bottom half, the glass part, to make sure it doesn't affect the sample. So during the cleaning, we use the sample holder, the blue one, and we put that into a large beaker, usually 1000 ml beaker. And we will do several steps during the cleaning with different cleaning solutions. So basically here we do is first we clean with the salt water with 30 minutes, and we put the whole beaker covered by the glove in the ultrasonic cleaner. So you will see later in the specific procedure. After that, we will change the solution to the DI water, pure DI water for another 20 minutes. That's the optional step. But if we do that, it makes sure the samples are cleaned enough. And the third step is we clean with the acetone. And finally, we clean with IPA. So all 4 steps are using the ultrasonic cleaner. And we just put them inside and do the 30 minutes cleaning. So for preparing the solutions, we usually in our lab we do the perovskite solution. So basically we put all these materials in the brackets. You can see there are 4 materials: MAI, PBI2, DMSO, and gamma B. We put them in certain ratios so that we know like what their concentration is. So here I put is the control group. That means the standard solution we will most oftenly do in our prepare fabricating steps. So we usually change some amount of the material to change the concentration and to test out if it gets the different results. But here the ratio is the control group ratio. So besides of that, we have PCBM solution need to be prepared as well. So we usually have 20 mg PCBM in 1000 microliter of the chlorine benzene solution. And when we prepare them, we put them on the hot plate for 70 degree, stirred overnight. So usually those solutions will take time to dissolve entirely. It took several hours to at most 8 hours, depends on different materials need to be dissolved. So here is like some basic idea of the fabrication procedures. So after we clean the samples, we will took the samples out of that sample holder and put them for the UV ozone first to let it clean and prepared for the spin coating of the first layer, the P dot layer. So for the P dot layer, we do it outside of the glove box, and we set the RPM for spin coating and time. So after that, we will etch with DI water and baking the sample at 140 degree for 15 minutes, and we will do another 20 minutes cooling to room temperature. After that, we will get the samples into the glove box for later layers. So here is the PVK layer we will do inside the glove box. So during that layer, we will do PVK solution filtered and first coated onto the sample. During the spinning, we will also put the toluene on top of the spinning sample to make another layer. And after the spin coating, we will put the samples on the hot plate for 80 degree for another 10 minutes. And then we will do the cooling again. So on the right side, you can see in that brown vial, that's the prepared solution. And those three samples are in black. Those are samples like already hotted or up like after the PVK layer already. So after the spin coating, it's like kind of transparent, but after heating, it will darken and be black, and you can see it's evenly coated, so it's like dark and in good quality. So after the PVK layer, we will just add another layer, the PCBM layer. It's also like going to be filtered first and then spin coated on top of the PVK layer. So the spinning speed and the time is set differently for this layer. So you can see like it will usually give like a very thin thickness. And after that, we will do another Rodmin solution on top of the PCBM. It's going to be very, very thin. Actually, we don't need to be very specific about the volume of the Rodmin. Since it's going to be very thin, we usually put only 50 to 60 microliters of the solution during the spin coating. And after that, we will etch with the gamma B. So at last, we will do evaporation to coat on the top with the silver. And for that layer, it's usually 100 nm, and we can control the thickness, and we can control the coating time, like using the our systems in the glove box. So after that, we can do the testing, like we will learn later. So here is my basic slides for the demo. So I will give you guys a real laptop now to discuss the steps we show in the slides. So if you guys have any question, you can ask at any time.
Thank you, Yushan. Is there any question on the slides from the student side?
Yushan, thank you so much for such a nice explanation of this fabrication process. First of all, I would like to know what is the area of this silver coating? Actually, it will define the active area of the solar cell. So, area of the silver contact,
You
I
mean
would like
the
to know.
silver? So
Yes, yes.
we use a mask for evaporation. So I can show you maybe the finished sample, so you can see. Yeah.
Actually, the active area is 0.13 centimeters.
Okay, 0.13 centimeter square.
Yes.
So, you are using shadow mask for this one.
Yeah, we are using shadow mask. Like we'll be putting 4 fingers for each sample. So we're using 1.5 centimeters square by 1.5 centimeters square sample. So using a shadow mask, we will have 4 fingers on each sample, each having 0.13 centimeters square area.
Okay, get your point. Thank you so much.
So if we do not have any other questions, I will left.
Yeah, please go ahead. I don't
Okay.
think so there is any question.
Okay. So I will like my colleague to record with another device.
Yeah, I guess you guys can hear me and see me as well. So here we are preparing the solutions for perovskite. Normally we do 3 kind of fabrications. Like we are trying to fabricate a tandem device. So the tandem device basically consists of 3 band gaps. One is the low band gap, which is 1.12 electron volts, and the second one is the medium band gap, which is 1.5 electron volt, and the third one is the large band gap, 1.8 to 1.9 electron volts. As you know, we can control the perovskite thickness and as well as everything from the spin coater, and you can control the band gap of the perovskite using the material. Suppose if you take the most common MAPBI3, that is 1.51 electron volts. That's the solution we prepared here. So this is a solution for perovskite. Like after some time, we're gonna filter this. The one you're seeing inside is the stir bar. So these ones are stirred overnight for at 870 degrees centigrade overnight at 4000 RPM.
Raja?
Yep.
I would like to add at this stage that to the student that all this processing is being done inside the glove box.
Oh yeah, sorry, I forgot to mention.
Yeah.
The one
So
I'm
and
holding
his
here is
hand
the nitrogen
actually
filled gloves.
two hand is inside the glove box and is standing outside. So
Can you
that is a
just move
nitrogen filled
ahead?
glove box which has a control humidity. Yeah, you can see now. Yeah. Thank you. Thank you.
You can see like the humidity inside is 20% right now. That's the minimum humidity you can get. And if you go to the panel over here,
So here you can see what is the oxygen level and what is the water level. So this is a continuous closed loop, like the air nitrogen actually is connected on the back side and it is continuously rotating. and it keeps the water and oxygen less than 1 ppm inside. So you can see the two glove box is interconnected, and all the chemicals are placed inside. And this is called the TNT chamber, from where you can add the bigger items. Otherwise, the smaller one that is just near to that, you can add yes here. So from here you can put all these small chemicals, and then it's a standard procedure and protocols you have to follow. Okay, so first you put the sample inside, then purge that 3 times so that it is having like lowest oxygen and water content, and then you just take that out inside the glove box from here. Yeah, so you just open it, and then you can take the samples and all these things inside.
So
Yeah, please continue.
this is the weighing balance which is already calibrated. Normally you can see this in gold shops, I guess. So this controls the precision of 0.1 mg. You can weigh from 0.1 mg to 700 grams here, and this hot plate can go up to 1000 degrees centigrade with you can see the spinning speed also. You just put the RPM here, it's going to stir the water, the metal is on top of that, it's going to stir them. So that's one of the function of this hot plate, to stir the material as well as heating them. And beside that one, that's a spin coater, which is also inside the glove box. It's by controlling the speed of the spin coater, like the speed of spinning, the centrifugal force, we are going to control the thickness of the perovskite. So thickness we can measure with cross-sectional SEM of perovskites as well as with AFM also. Normally we deposit like 300 nanometer or 300 micrometer thickness. And for P.PSS layer, we are going to do outside. So basically we are doing a PIN structure. So in PIN structure, the first layer will be P layer that will be outside the glove box. And the second one is the I layer, intrinsic layer, which is perovskite, which is done inside the glove box. After that, that's the N layer, which is PCBM, basically carbon, which will be done inside the glove box. The second glove box you are seeing, it consists of
Yeah, so this one actually you see that this is thermal evaporator. Okay, so you just insert your 2 hands, and then it has a door, so it can slide. You put your final device inside with the physical mask on, and then so you have few openings there. So through the openings, the physical mask, the metal is getting deposited inside. So that is a final device where you can prepare that. So generally we keep the two things, like one is kind of a chemical processing, another one is a physical vapor where we deposit this final metal contact. So these generally two chambers are separate.
So to add to Dr. Mukesh, like the chemical process, in the glove box too, we have different modes. Like we have purging mode, we have like circulation mode. So circulation mode, it will circulate whatever the atmosphere inside the glove box. In purging mode, it will just take away the old nitrogen and get the new nitrogen into the glove box. So we are using 180 liter liquid nitrogen cylinders to purge the nitrogen into the glove box. For some materials, you need the circulation mode, and for the other materials which will accumulate any solvents or something, then you need to purge it while fabrication. So that's the two modes available in this glove box. Just we are gonna weigh some material. We already prepared solutions for you to show the demo. It's just to show like how you weigh the material. So you can do it in both ways. Like you can weigh directly in vial, or you can weigh on the weighing paper. So here is the weighing paper. We can weigh in the weighing paper and put in the vial there. So I prefer this step. So just put your vial in the middle gently. This is called tear. So tear it to make it 0 mg. So you can see that is 0 mg. And I'm gonna put some FEI into that one. So FEI is ammonium iodide, which is used for tin-based perovskite solar cells. So the weight right now is 126.8 mg. The weight I want is around 138 mg. So I just need to put more 10 mg of the FEI. Just take a little.
And
it
you
in.
should be very precise actually, because you
Yeah.
can see and you see that,
That's
yeah, 1.3.
31. So you need to be like, you need to know how much amount need to go in. Like once you're, if you're not sure, just weigh it in the weighing paper first, then weigh there. Because as you know, every material's molarity is different. Every material weight is different. So depending upon the weight of the material, you need to take the amount of material over there. Some materials are very light, and some materials are like having more weight for the less content.
And Reja, many times actually when we used to do that, so static charge is a big problem.
Yeah.
So how
That's
you how guys you do like to avoid that?
So we counter it by turning off the, like one of the main problems with blowing out is circulation, and one is like this. We don't use these as magnetic ones right now. We use the stainless steel. The
Okay,
static
okay.
charge mostly appears with some metals, so we use the plastic or steel ones to counteract the what are the static charge. Yeah, you are right, Dr. Mukesh. Like that. That's the main problem here.
Many
So I
times
just
we,
need more one
we
and
saw actually that powder is going here and there, and then we
yeah,
realize actually there's a
that
problem of the static charge inside because there is no moisture.
yeah, true. That's why we don't use any metals inside the glove box. Most of the time we avoid using metals. So I need 138.6. It's 138 right now. So I just need to put more 0.5 mg. If the material is not precise, you are not going to get the desired results. We're almost there. You can see here, like we exactly got the weight over there, like 138.5, 138.6. So that's how we are going to weigh the materials. So now I mixed tin iodide and FEI. Now I need to put some SNF2 in there. Then after that, I'll just put DMSO. Like the solvents we use are like Gamma B, DMSO, and DMF. So dimethyl. So these we call as parent bottles. Normally we don't directly take from the parent bottle. From parent bottle, we will dump that into a small vial so that we don't contaminate the entire vial if we have a problem with the procedure. So we
Yeah.
will dump that into a small vial, then we will take into this vial here. So these are the pipettes we are gonna use. This is 100 to 1000 microliter pipette, and this one is 2 to 20 microliter. So for dripping the perovskite, we are gonna use 20 to 200 microliter. Normally we use 60 microliter of perovskite solution when you are dripping the solvent. And for anti-solvent dripping, we are gonna use 100 to 1000 microliter because we are gonna drip 160 microliter of anti-solvent during the spin coating in order to crystallize the perovskite.
So measuring the like material and keeping all these things like using this spatula and this like other things. So you have to be very, very precise and very careful about the contamination.
Yeah. See, like all the time I was holding it like this so that I don't touch the tip anywhere.
Yes, yes.
And I'm done with this one, so that's not a problem. Now I can just after this, like once you weigh the solvents or solution like materials, you're gonna take it out from the glove box. Then you'll clean them for the next use. You're just not using that every time. You're gonna clean them every time you use. The more cleaner the glove box, the more better the films will be. Even the spin coater we clean for every fabrication, because the lesser thickness of the perovskite, Even a small contaminant can just change the morphology of the perovskite everywhere because we are using the centrifugal force to spin cone.
So Reza, I think just for better cleaning, you just put this paper and the peripheral of this inside this spin coater was okay. So you can
Yeah.
easily remove that after the.
Yeah, I can just see.
Yeah.
There is aluminum foil inside that one too, but I prefer
Okay.
paper because it will absorb all the materials, so there won't be
Yeah,
any
yeah,
cross
yeah.
contamination.
Yes, yes, yes.
We will show you how to trip the perovskite since we already prepared the solutions for you. So now this Uchan guy is gonna deposit our whole transport layer outside the glove box in the fume hood. And I'm gonna transfer him to there. Meanwhile, if you got any questions with the glove box, feel free to ask Dr. Mukesh or me because Dr. Mukesh also worked a lot of time here. So if there are no questions, then we are gonna show you how to deposit P.PSS.
Amit, is there any question from the participants?
Let me check, sir. 1 minute. No, sir.
Okay, okay.
So hey, everyone. So before the P dot spin code, I will show you guys like how to get the sample clean. So first, you can see like in here, these are unclean samples like from the manufacturing company directly. So we need to be very careful when we took them out. So you can see we just pull the this strip out very carefully, and the samples are like on top of it. So you can see like they are aligned here. So I will just use several for demonstration. So I took out 3 samples here. So be carefully when you put this strip back to the cover. And here is the multimeter I showed you in the presentation. So here we want it to be in this mode. And when you touch the conductive things, it will beep up like this. So you can see the numbers. That is the resistance shoot, and we want to use it to check the conductivity of the FTO side of the samples. So you can see like there are 3 samples. They are like discussed earlier. The FTO side is on top with color, and the bottom transparent part is pure glass. So if we put both wires like on the top side, it will either beep up or not. Like if there's no sound, that means they are on the glass side and we are fine to label. But if I flip it up, so you can see there's sound and there's number on the multimeter. That means it's on FTO side on top. So in that case, we want to label the number on the glass side. That means we need to change this side. Now, these all 3 samples are on glass side, and then we are ready to label the numbers.
And this
So
is
to
actually I would just
label,
like to add. Sorry. Yeah, please continue.
to label the numbers, we will use this diamond pen. So you can see the tip is very hard and it can write numbers on the glass. So for the labeling, we will usually write a number. So like number 1 here, followed by a horizontal line. In that case, when it's flipped, we can differentiate like which side is the glass side. Like if we flip up, the horizontal line is at front, so we can see
is the FTO side. So we will do the spin coating always on the FTO side. That means the horizontal line in front for every step. So we will do the same for all the samples, like 2 horizontal line, 3 horizontal line. And we will usually do 24 at the same time. Why we do 24? Since in the sample holder we discussed earlier, there are like 24 um, 24 positions to hold the samples. So after we label them, we will put the samples carefully into the sample holder and then put the sample holder in this beaker. So these are cleaned samples already, so you can see there's samples aligned at the sample holder. So you will put the FTO side at the bottom and the glass part like on top to make sure it's fully cleaned. And since you will use a tweezer to take the samples out, so you always want the tweezer to grab the glass side, not affect the FTO. So for the cleaning, once you put the sample holder into the beaker, we will use the ultrasonic to clean the samples. So here's the ultrasonic cleaner I showed you. So you can see there are 2 readings. The left one is the temperature of the water inside. The right side is the timer. So our first step is to put the dry water and the salt as the solution inside the beaker and outside the beaker. So outside the beaker, we will just put the water to let the inside the liquid level and the outside the liquid level to be equivalent to make sure the cleaning quality is at the best. So once the level is equivalent, we will put this glove on top of the beaker to prevent any dirt or other mixtures to get into the solution. Then we will change the setting time. So the first step is 30 minutes, and then we can start. So after that, after the cleaning, you will see the temperature increases. That means the water inside increase the temperature. For the cleaning purpose, we will change the water from this valve to get the water out and change the water like the room temperature water inside the cleaner again for the later cleaning. So the second step is dry water for another 20 minutes. It's the same procedure. And later we will use the acetone and the IPA to dissolve the organic things inside the beaker.
So here I would like to add this FTO actually is a transparent conducting oxides, okay, and it is having a transparency more than 80% in entire visible region. So that's how actually we are having like this one of this layer, and it is so transparent it's very difficult to see if it is coated uniformly over the glass. So that's why actually the point is marked. Yeah, please go ahead.
So this is a fume coat. We will do spin coating for the P-dot layer, and we will also like changing the acetone and the IPA like inside to prevent like something spill out and to protect of ourselves. So here we kept our acetone and IPA. So this is acetone used for cleaning. So every time we will use it, we just take it out inside the fill hole to pour it into the beaker, and the same for IPA. So once you want to change the acetate and IPA, you want to pour them into the waste bottle. So this waste bottle are kept for acetate and IPA and all halogen waste. So now I will show you guys how to fabricate the P dot layer. So these samples are already cleaned. And I will uncover it and use a tweezer to take out the samples we want to use. And first, we need to turn on the digital UV ozone system that I mentioned. You can set the time and the temperature. And when you do the UV light, you can see in the dark. And we will also use the gas to blow some liquid on top of the sample, so that after that we can put the samples under the UV system. So you can see the readings here. It's the pressure. So if I open it, the pressure will change. And we use this. You can see the glass blowout. It can blow off the liquid on top of the sample. So this is a tweezer we will use to get the samples out. So you always want to grab on the glass side, and when you took it out, you want to blow it with the gas to make sure it's dried up, and then put the dry up samples on this plate. So you will always make sure the FTO side is on top. So that means the horizontal line is front of. So like this should be number 7, right? And the number is reverse, so that means the active side is on top. So I will take maybe, let's say one ball. So once we have samples ready, we will like close it. And start. So to make sure it's already operation, you need to like close turn off the light, and there's some UV light. It's visible, like you can see it's working. So if you close it loosely, there will be no light like this. So you need to make sure it's working.
Are you flowing any oxygen there inside the UV?
No, I don't think so.
Okay, so that is the plasma created with the normal air. So this UV actually, this what the function of that equipment is, it is having a wavelength in the UV region, and it is creating this like reactive oxygen that is helping to clean the surface.
Yeah, so after the clean surface, we can do the spin coating, and don't forget to put back the samples you roll. And during the winter time, I need to stir up the P dot solution. So we usually keep our P dot solution inside the fridge to keep it fresh. So we will use another empty valve to prevent the contaminate. since it's a new well, you don't need to clean it very carefully. If it's not a new one, you need to clean it with acetone and DI water and dry it up. So before you use it, you should better use gas fluid to make sure the dirt or something else inside it. Remember to turn off the valve each time you use the gas. You can see the pressure drops to 0. So that means it's closed. So every time we will not use very much P dot, so we will just pour a few drops inside the valve. You can see like it drops out very slowly. So each time we can keep it fresh in the fridge or like reuse or use the new solution for the fabricating. Since we fabricate a lot, so we can keep them in the fridge for the next use. And for this solution, we will use that ultrasonic. So we'll keep this valve inside for another 5 minutes. So since I brought some water, I need to add some more water inside. You can see the temperature is absolute temperature, so we are fine. We're fine. We will use the syringe and the filter. It's a 1 ml syringe. We use it to take out the P-dot solution and do the spin coating. So we usually put this filter on top of this syringe. So every time we use a new syringe and a new filter. So this is the spin coat, another spin coater. It's outside the glove box. We will use this one every time for the P dot layer. So you can go closer to the setting. So you can see here, we set the spinning time and the spinning speed, and there's some acceleration, I think. So if you want to change it, you can change it from the raw mode to like edit mode. So this is edit mode. You can change the numbers. You can change the RPM and changing the time. So usually we keep the P dots the same, but when we do other layers, if we want to change the thickness, we can either increase the spinning speed or like decreasing the time. So we will change these settings. Like it depends on what we will change for the fabricating. And you can see this one is also like prepared by cover. We need to clean it as well. And after the P dot layer, we will use the DI water to etch it with the swab here. And after etching, we will dry it up, use the swab. So this is basically we will did for the like P dot layer. So after for time purpose, I made like a stopover layer for the samples and for the cleaner so that we can proceed. I'll focus on this.
So that is the first step actually is going to happen. That is a P.PSS. And that is actually, you can see on tip of this syringe there is a filter. So that filter actually, the purpose of this filter is to just filter out any big particles that can come from this P.PSS solution.
So now you can see there's some solution like in the syringe, and we will keep it close to us, and to make sure it's not like dropping out, we cover the paper, and we change the paper after this. So now we can turn on the motor for spin coating. And yeah, we need to turn on the gas again to clean the surface. So make sure you do it every time, like for the fabricating.
Now you take this sample gently and just place on top of the spin coater. And once you press start, so there is a vacuum actually that suck this substrate.
So you can see if this number changes, that if we set 0, it means it's not vacuum and can adjust. If you press it again, the number changes. It means the sample is still on top of the spin coater. Then you can blow it to blow away the liquid and the.
So there is a
vapors
final
of
blow actually
pulp.
just to remove any particle from the substrate.
So now we can everything very carefully. So usually several drops.
You just cover the entire substrate with this solution, close the lid, and then start the program.
So you can see it's like covered, and then you can close the cap. And then we can start. Make sure the settings are correct before you start. So you can see here, it's fading very quickly.
It is rotating with a 4500 RPM, and it will have the fixed thickness. So there's a time left. And here you can see actually V vacuum, that is 25. So if this is not there, so it will not start rotating. So if there is some issue, then we need to check the vacuum. So Eugene, what will be the thickness of this PSS at this RPM?
30 to 40 nanometer.
40 nanometer, okay.
40, yeah. So you need a petri dish to keep the samples after the spin coating. So once it's done, we can open it. Remember to unvacuum it and be very careful to this out. So since we need to etch it, we want to transfer it onto this plate. So now we will transfer the samples to the plate. To you can see like the spin coating quality is very good since like it's transparent without any particles and it's evenly coated. We use the cotton swab to and dip with the GIAN water for the etching. So we want to hold with the pen to keep the sample stable. And then for etching on the right side of sample very carefully, and you need to etch it steadily and some force to keep it etch out, and you try it out with another. So after finish that, we can put them on the patch dish, and then we can do another sample. So usually you can also do the etching while you are waiting for the spin coating for the next sample, so that will be now we are doing the second sample. Procedure is the same. So basically during this time we can do the etching. So that's like more efficient if we can do ask the samples etching during the spin coating for the sample. Meanwhile, like, you guys have any question with you? Yeah, you guys can ask at the first shop.
Yes, Amit, if participant have any question during any step, so they can ask. Okay, Syed, I can see actually has a hand raised. Is it correct?
No,
Amit?
sir, he has raised it earlier. He has asked
Okay,
it question.
okay.
Yes, sir.
Okay, okay.
But if there are another participants who wants to ask questions, they can raise their hand. We'll unmute them for a while.
Yeah, Yushan, I have one question, one basic question. Actually, I would like to know you are using PE.PSS directly or you are diluting this solution, this in particular solution, in some solution.
This P.PSS is the direct from company.
Okay.
Normally when like there are different types of gold transport layers, like you can use nickel oxide, you can use copper oxide, you can use like depending on the structure too, like if it is NIP, you are going to use SnO2 as the bottom layer, and the top layer is mesoporous TiO2. Since it's the PIN structure, we are using P dot PSS to align the band gap. That is called band alignment.
Yeah.
The band, we are using P dot PSS.
Sir Sayed has raised his hand again. I am unmuting him. Mr. Sayed, you can ask.
Yes, sir, yes, sir. Sir, why we are cleaning the side of the sample by this tissue?
Yeah, that's a good question. So if you can see the final sample, these are the old samples. You can see there's the edge side. So we need the bottom electrode as well as the top electrode to test the sample. So you don't want to have anything in the bottom electrode. That's why we will edge the side.
Okay, thank you.
So yeah, I hope it is clear.
Yes, sir, yes.
Yes, good.
So now we are gonna bake it, like that's we call it.
Yeah. So after the spin coating, we will keep them on the hot plate and heat them up to 140 degrees for 15 minutes. And after heating, we will cool it down to room temperature. And we will cover it to prevent any contamination. So that's the P-dot layer. And we will do other layers like inside the glove box.
So the first layer is almost ready. So we need to just anneal it at 140 degrees centigrade so that
Sir,
this
I have
water content is out.
So I have one doubt actually. Is this IPA cleaning is the final procedure or it is followed by cleaning in DI water also?
The
Depends,
cleaning
like
is
cleaning mostly depends on the preferences, because IPA is the last step normally we do. But some people will again clean it with DI water. But we don't see any difference in the samples between DI water and IPA.
so there is no uniform as kind of cleaning process or different like you can apply different kind of a cleaning strategy depending on your chemistry that you are doing.
Okay.
So you can see how the hand actually is being inserted inside, and gloves is on. Sometime we like we can have the gloves even inside the, like once you put that hand inside, so sometime you can have the gloves also. So you have to be very careful, otherwise you can puncture these gloves and then the gas will be out.
So this evaporator, normally we will use it for depositing silver. Like you can actually deposit any material you want. So here you see the film deposition controller. This is the deposition controller we will use. If you see the process menu, we already optimized these things, the process 1, process 2, and process 3. So go to the film menu, edit. So the three things you need to know about a material, like when you are going evaporate or do the vacuum deposition is the density of the material in the Z factor. Normally, this will be available with the manufacturer, but if it's not known, there are some particular ways to calculate this Z factor and density. If anybody is interested to deposit some material, I can certainly share the thing. And the tooling factor. So the film tooling factor basically depends on the height of the sensor to the hot. I will show you what it means. Go to the functions. So here is my evaporator screen. The basic evaporator layout. You see this pocket 1, pocket 2, pocket 3. So these two are pocket 1 and this is pocket 2. Basically, we can cooperate 3 materials at pocket 1, you can have 1 material. Pocket 2, you can have other material, and pocket 3, like this pocket 1 of source 2, you can have other material. And these two, the black ones are called shutters. So shutters are used to close the materials. Let me go to the evaporator. And this is all automated system. So most probably you just go to the evaporator functions and open the evaporator in other, which will unlock this scene so that you can open the evaporator. As you can see here, these are the 2 shutters and these are the 3 sources. So these are going to supply power to this to heat up these elements. So let me show you. This board particularly used for depositing C60, the electron transport layer, like we can do in both ways. C60 is the sublime C60, which can't be deposited in solution processing. We can deposit with evaporation. You see, there are different boards for different materials. This board is for C60. This board is for silver. And this is a crucible here. So if you can see, this is called as crucible. So this crucible
where you generally
is
load the
called,
material.
yeah. So this crucible is depositing PCP. So normally in the medium band gap solar cells, we use PCBM as electron transfer layers. But when you come to the low band gap, the band alignment with PCBM is not that good. That way we will use sublime C60 to evaporate in order to have a good band alignment. In the tunneling junction, normally in the medium band gap 1.5 electron perovskite, we will use as rhodamine. And for the low band gap perovskites, we will use BCP as the tunneling junction in between silver and BCP. Sorry, silver and electron transport. So basically, you have 2 things here. One is a medium band gap and one is a low band gap. It depends on your function, which material you want to optimize. And the one you are seeing here, this is the sensor. So the sensor will be mounted here.
Raj, this
This
this stage is okay. So that is a sensor for this quartz crystal monitor.
Yeah, this
This
stage is the last
stage
step
you
for
have. This is
depositing.
heated one.
Pardon?
This stage where you hold the sample final device, you deposit at room temperature, correct?
Yeah, we deposit at room temperature.
Okay.
But we will increase the heat inside the material, like inside the evaporator. Normally we are not gonna see what is that, but it's gonna heat silver. So for heating silver, it's not gonna be room temperature.
No. The substrate.
Yeah, the substrate will be at room temperature because the substrate will not be on top of it. Substrate will be here.
Yeah.
So your deposition material gonna evaporate from here and reach the substrate. So the purpose we are creating the vacuum is to create the mean free path, like to create more mean free path for the electrons, so that it won't bombard with other atoms, which are air or nitrogen, so that it won't diverge or it won't deposit nitrogen on top of the material. So basically, we are gonna put the samples here upside down. So these are the masks. Like before some time, I think Dr. Mukesh asked me, like, what's the area of the sample? So if you can see the fingers over there, each finger is having 0.13 centimeter square area. and the small finger over there is the anode. And this is for the large area samples. This one we use for the large area samples. So these piezoelectric sensors can measure the thickness up to angstrom, like kilo angstrom and angstrom. So we will put this piezoelectric sensor over here to measure the thickness. So whenever the sensor comes below 90%, when we can see the sensor health here, the film system per sensor info. So you can see the sensor life. So once the sensor life comes below 90%, that means the sensor's lifetime is over. Means there is a material deposited on top of that one. Then you will change the sensor over there and place the new sensor to deposit the new materials. So all you need to know for depositing a material is mostly these three parameters. Tooling factor. Tooling factor you can adjust with a equation like actual tooling and tooling used here and actual thickness and the thickness you got from the sensor. And density and C factor normally is with the material. So if you know these three parameters of each material, then you can deposit almost like which can be deposited. It's not like you can deposit every material, which can be deposited with evaporator. You can certainly deposit here. So
Yeah, it
this is the
depends on
final
the
step.
melting temperature of the material that you are going to deposit.
So this is just the basic introduction of the evaporator. Anyway, we are going to deposit silver here for some time, maybe today or tomorrow. I'm not sure, like the time permits. But the Eugen is filtering the solvents. Questions for evaporator?
So you can see that Yuchen actually is even wearing the gloves inside, even working that inside the glove box. So you have the thick gloves, that's the black rubber, and then inside gloves. So that is just to avoid any contamination to these gloves, because it should not be contaminated, because every time you will use these black gloves, that's the baseline. So you have to be very careful about the contamination while processing these solution process perovskite solar cell. So sometime when we say that the reproducibility is not coming, so that means actually unintentionally we have done some mistakes during the processing of any one of the layer, or there is some contamination problem.
So now we can see the valves prepared earlier. So prepare the valves. One is for PVK solution. The other is for the PCBM. So we need to filter these two prepared solution into the new valve. So to do that, we take in the syringe and we use this red cap filter here. We keep this on top of the new valve to filter the solution.
So that is
So
again
first
actually
we will
filter,
do,
just to filter out the solution or any big
yeah,
particles.
first we will do PVK. So be careful when was
That's PCBM.
this PVK.
Very good.
Okay, so don't mess up. We need to put the PVK solution inside the PVK filter and put it on the flat surface. And open the PVK solution. Use the syringe. It's a new syringe. To be very carefully. To call the PVK solutions. So since we are doing the demo, I will not use all solutions. So be very careful. You can keep it on the hot plate for now. Since there's actual solution inside, it will stir it. So keep it vertical and oh, it's upside down, sorry. So make sure the right side is on the top. I may use another one since it drops. So push it very slowly, otherwise it will spill out. You can see inside the well, it drops very slowly. Don't rush. It takes time to filter it. So now our solution is ready for spin coating. And we put all the waste inside the beaker so we can take it out and clean afterwards.
Yeah, there's a limited space actually, so you have to be very and like it should be very neat and clean inside.
So now we can turn on the motor. And turn on the vacuum. So always turn on the motor first and turn on the vacuum later. Since if you do it reversely, the pressure will be. So here we have the scene interface. So now you can see the RPM and the time is different. So basically in this step, we have two steps in this program. Since we have 20 seconds followed by 60 seconds. For the first 20 seconds, it's 750 RPM. And for the later 60 seconds, it's 4,000 RPM. So I will use a sample inside the floor box. It's not the same samples we just did since they are heated up outside. So those are basically samples after P dot layers, like after heating. And we always want to use the fresh sample, but for demo purpose, it's not that fresh. So we will use tweezer inside the glove box and took the samples onto the spin coater.
So participants, you have observed one thing that most of the petri dish is covered with the aluminum foil. So it's just to avoid unnecessary exposure of the samples to the environmental light.
So always make sure the P dot side is on top. So you should look at the numbers to check first. And lay it at the middle. Vacuum it. Then use the blower, this small blower to blow it, blow out the particles.
So you can adjust the amount that you want to just keep it.
To 1000. So we use this yellow tip. We use this yellow tip here. Carefully to keep it on the and use the solution. So you need to drop it very carefully. So we usually drop it in circle to make sure it covered each place on that sample. And then we can keep the pipette hand up, not touching anything, and we can reuse this again, like for the next sample. And then we need to use another pipette prepared with the other white tipper. Since we need to drop the coloring, We set it to 160. And then we can use the tolerance. Yeah, okay, that's fine. So make sure you took the tolerance and get 160 from the tolerance. You need to prepare it like before the spin coating, since you will drop them during the spin coating. Then we can start the program. So once the first step finish, it will restart with another 60 seconds for the second step. So prepared for that 40 seconds countdown, then we can add the tolerance on top of the sample.
What is the purpose to add the toluene at this stage? Vishan?
What's that, Dr. Mukesh?
Just asking like the purpose to add the toluene.
The purpose of toluene is the anti-solvent.
Okay,
So-
okay. So it will enhance the crystallization.
Crystallinity of it.
Okay.
So normally we prefer single crystalline materials, as you know, they are
Mhm.
efficient. But perovskite is a multi-crystalline material with shorter
Yeah.
grain boundaries. So we want lesser grain boundaries and more grain.
Yeah, solvent anti-solvent actually is one of the approach people use to enhance the efficiency.
So it depends on your dripping time too and your lab condition. Sometimes the 40th second give you the bigger grain. Sometimes the 20th second will give you the. When you are starting to fabricate it, how much thickness you want, you can adjust with the molarity or the spinning. Now, one more thing, the dripping height and dripping speed. So if it, there are like three types of solvent, like chlorine type 3 solvent, toluene is the type 2, IB is the type 1. So type 1 solvents need to be.
Sorry to interrupt you, Pujan, but hello. Sorry to interrupt you, Pujan, but can you keep the mic closer to you because we cannot
I'm
hear
sorry.
you properly.
We all speaking from the same mic, that's why there's a problem. So,
Okay.
yeah, if you can hear me.
Yeah.
So there are three types of anti-solvent we use normally. So type 1, type 2, and type 3. So type 1 IPA type of solvents need to be dripped very slowly. Type 3 need to be dripped very fast.
Mm-hmm.
And type 2 need to be dripped in the moderate speed. There you form the crystallization.
Yeah, so after the spin coating, we can take this out. So this time I will just do one sample and we can directly transfer it onto the hot plate. We want to heat it up for 80.
Take out those wires. That's right.
So we can see actually how it's changing the color.
So we set it to 80 degrees. It will rise up in temperature. And we can turn off the RPM for now. Since this sample is not that fresh, so basically if it's in good quality, the whole sample will be darkened like entirely. I will show you the other yeah, it's increasing.
Yeah, so after Elling actually start to show the dark color, so that means actually it can absorb the light.
Over there. Stay over there.
So you can see those samples are fabricated and heated after PVK layer. So it will be darkened and entirely black. So you can check the quality, like for different samples. You can see like they are in different quality. So after that, we will do the PCBM layer and the rod mill. So this sample will be heated up here for 10 minutes and then cool down to room temperature. Then you can do the PCBM layer. So it takes time. So now we will just use these samples here. So now we will use the other syringe to filter the PCBM solution prepared. So this is prepared PCBM solution.
So PCBM here we are using as a electron transport layer.
So, syringe. So it's the same procedure as the PVK solution. Filter it very slowly and let them go into the new valve. So now we want to change the tipper since this change the tip since this tip is for the PVK solution.
So inside you need to put the things according to your convenience, where you are best convenient to pick the tip, solution, and all these things.
Jobs. So now you can see the interface like spin coater. We need to exit and use another program. We preset the program. So we enter it. You can see the interface change for time and spin speed. And it's the same way you put the sample. Make sure the correct side is on top. And vacuum it. Blow it. Then drop the PCBM. It's the same with PVK solution. You drop it like in circle to get them evenly on top of the sample. Then you can start spin coat. So after this step, you will need to take the samples out onto the hot plate, heat up for 80 for another 5 minutes, and then cool down to room temperature again. So after it's cooling down, we can do the rod-on step. So for time purpose, I will just use another sample for the rod-on demo. So we took another sample. Make sure it's on the right side. And remember to change the program. So we use this program 6. You can see the time and the spinning speed also changed. So it's now like 40 seconds. And vacuum, blow it, and change the tips for the robbing in dry IFJ. So this is the solution we use. It's in red color. It's easy to differentiate. So usually this layer is very thin. So we put a very small amount of the robbing, and basically we can put in like 50 or 60, right? It will not affect that much as long as it's very thin. So after this step, we use the gamma P to etch it inside. And we took the photon swab. So carefully took this out on a plate. I didn't taking the plate, so I'll just use this petri dish for now. So place that and etch the thin side as we etch like etch the DI water outside. So it's still like the right side of the sample. And this time, you just use the gamma B. And it's the same procedure. Once you finish the etching, you need to dry it up as well. So carefully use the tracer to grab the sample on the right hand side. It's the same as what we did outside. And just use the swab to etch it on the right side and then use the dry swab. This is the right side. Yeah, yeah, that's fine. Yeah, since usually we use the plate, it's like it's in different color. Since I do it on the petri dish, it's like transparent. It's very hard to see. So now you change the swab and do it with the. You dry it up, and now use for.
Now this is ready for metallization.
Yes. Yeah. So it's basically everything we did in the glove box. It's just in the middle step we skip the waiting time and the heating time. So if you have any questions, you can ask. Since like it's almost the time.
Amit, is there any question from the audience?
Audience are allowed to ask the question. They may raise their hand or they can post their query in the chat box or question and answer. So, Poojan, I have one question. Please tell me the full form of PVK.
Perovskite. We just use the abbreviation.
Okay.
Because the vials have a short. The labels on the vials are very small, so you can't write the full.
Yeah, yeah. It's just like convenient to use some several characters.
The doubt was only due to here we are using a polymer called PVK, short form. So I was little bit.
Yeah, and we need to turn off the motor since it's very noisy.
Any other questions? If not, we can just close it down. I think it's late over there, right?
Yeah, so maybe you can go to metallization. So metallization you already explained, Raja.
Yeah, Raja already explained you.
Yeah, so maybe like once you can just try to put the like final device, because there is a trick, because this side will be anode and then rest of that here. So you can just demonstrate once to this.
Raja, sorry. Raja had a meeting, so he just went away.
Okay.
Yeah, so
just to keep the evaporator from contaminating, we just make sure that only one person operates the evaporator. So only Raja does it. So he just went.
Okay. So Raja has already explained about the metallization. So the clean part that you clean from one side, so that is one electrode, and then the rest of the electrode will be on top of that. So once you characterize, so that is on final day. So you just make a two contact. One is on the bottom and another is the top, and then you shine the lights, and that's it. You apply the voltage and see the current.
Yeah, and if you want to see, just a second.
Yeah, you can.
can just show you. So here you can see.
Yeah.
They look like this. This is just weird, but just in case.
Mhm. Good. Amit, is there any question from the audience?
I want to like ask one more question, sir.
Yeah, please go ahead.
Actually, if we do this carbon 60 C60 using thermal evaporator, and by the same evaporation system we are doing this silver or metallization part. So is there any chances of contamination during metal deposition or C60 deposition due to other like metal deposition or?
So actually this is a sequential deposition. So you are doing first C60 and then you are going for this metal. And since you are using the separate source, okay, and this high vacuum, so all these things actually is going as Reza mentioned. So mean free path is very large. So in 10 to power minus 6, the mean free path is about a meter. So they just colliding the surface. So they are going just straight. Okay, so the contamination issue may arise if there is some high energetic silver and then it is like kind of a re-evaporating the carbon C60 from somewhere else. So
Yes,
that's how
sir.
actually it is room temperature process and we are
Only
not
depend.
heating anything.
Okay,
Yeah,
so
so it is.
the degassing is can play the role in
So
contamination.
at this pressure actually 10 to power minus 6, the degassing actually is minimum. Degassing means if once you are heating something, and since at a time you are hitting one source which is a source of suppose silver, and since you are not heating C60, so there is no cross contamination issue.
Okay.
And we always keep kind of a verticals between the 3 different sources, so they do
Yes.
not see each other.
Yes.
So Mr. Said wants to ask question. Mr. Said,
Yes, sir. The question is that I have seen from the samples, the contact width generally is very thin, but here the contact width is little bit thicker. Is there any significance of that? The
We
front.
prefer the contact length to be smaller, but more the smaller contact, you can't get the better. Like when you are doing IV, like what we are going to show tomorrow. When you are going to do IV, you're gonna attach that to the clips. So once the contact is very thin, you can't get the proper attachment over there. That's why we use 0.13 centimeter square. But by using a mask, we can reduce the area to 0.04 centimeter square. The intensity area we can reduce with a mask.
Oh, okay. Generally, for the silicon solar cell, we find that there are multiple fingers and bus bar is there. So that's why a question arises that there is no bus bar like that. All the fingers are thicker like a bus bar.
Yeah, true. Once we go to the commercialization, yeah, there we need to use because to save the materials and all, we use the bus, and to collect the proper current from everywhere, we use more number of bus bars than here.
Thank you.
Any other question?
Yes.
another
Wonderful. This
question.
bus bar is a back contact or front contact for that?
Back contact for this.
Okay. So light is coming from the glass side.
Yes.
Okay.
So we have one question from Miss Pooja Chaudhary. I am unmuting her. Miss Pooja. Hello. Okay, let me just read her question. She was asking, in silver deposition, is there any shadow region forming in the evaporation process?
Shadow region, like we created that mask, and that is the depositing because of this shadow. So it is a physical mask, and so shadow actually it is, since it is a vertical, so there is no shadow of the mask. Shadow in the sense like it's a completely different thing, like where you create a shadow and deposit a nanostructure. So that is different technique which is known as the glancing angle deposition. So here there is no shadow. Instead, like there is a vertical things, and where there is a mask, there is no deposition, and like there is no mask, then we have the deposition of the metal that define the active area and all this.
Thank you, sir. Probably you have given the answer. We don't have any questions, sir.
Hello, sir.
Yeah, say it. You can.
Yes. See, I think the shadow comes from the, if there is a finger from the top contact, I think light coming from the glass side, and whatever the contacts deposited by the thermal evaporator, it is a back contact, right? Am I right?
It's the back contact. Yep, true.
So
Actually, I can answer the question in other way, maybe, because the shadow mask we are using is very thin, so the contact is all like the surface is almost direct path with the silver you are depositing, so there is no chance of getting shadow over there. And like once fabricated, we can use the vernier calipers or something to measure the thickness of the cell. Like once you get the efficiencies and everything, you can get the efficiency of the cell. And moreover, we will use a mask in the objection of sunlight to get to reduce the area to 0.04 centimeter square in order to avoid if there are any particles or something in the path.
Sir, I'm unable to understand one thing, that if light coming from the glass side, so first like it is ITU coated glass or FTU coated glass, so light penetrate through the ITU or FTU, then it comes to the absorber layer, right? Am I right?
Yes.
So why instead of the finger, why on the back side, I think the complete metallic layer should be more perfect for the structure, or the finger like a structure is more perfect for the structure?
Sayed, actually the problem is optimization. Like instead of putting the metal all over the backside, it's wastage of material. If it depends, actually, suppose I make sure the collection of the carriers only from the one finger on the back side. So I will prefer to do that, because in that way I can save a lot of metal.
Okay.
Yeah.
That's why I thought that what is the purpose of that? That's why question arising.
Okay. That's good question.
Thank you, sir.
Any other question, Amit, from the audience side?
Sir, I think it is all clear now. So I would like to thank Mr. Rajasekhar, Poojan Kaswekar, and Yuchen from
Thank
Professor
you very
Chow's
much,
lab.
guys. Actually, it's really wonderful, and you just showed the way actually we used to do in the lab. So I hope all the participants got benefited out of that. And thank you
Yes,
very
sir.
much once again to everyone.
Actually, we never see such a nice online representation or demonstration
Yes,
of
that's
fabrication.
really very nice. Actually, they have shown individual step and very minute details.
Yes, sir. It was indeed a great learning experience for each one of
Yeah.
us. Thank you, Rajasekhar,
Thank you very
Poojan,
much.
and Yuchen.
I guess it got a good insight into what we are doing in the lab. And feel free to send us any queries if you have. So we are good to answer. Not a problem.
Yes, sure.
Yes,
Thank
Dr.
you.
Mukesh can reach us anytime. Thank you.
Thank you very much, guys. Thank you.
Thank you. Have a nice day. Sorry. Good night for you guys.
Yes.
It's day. See you.
Yeah, Amit, if there is no question, and so we can close now.
Yes, sir.
Okay.
Thank you.
Okay,
Thank
thank you, sir.
everyone. Thank you. See you all in the
And
morning.